SpaceX is working toward an engine so powerful that it could push rocket design into an entirely new era. According to Elon Musk, SpaceX isn't treating Raptor 3 as the finish line. The next publicly discussed goal is a future Raptor capable of roughly 300 metric tons of thrust. Stack 33 of them together and you're looking at nearly 10,000 tons of force leaving the launch pad. That's not a rocket, that's basically a controlled explosion. And if they actually get there, it won't just be another upgrade. It could be the point where economics of spaceflight start to look very different. This raises a question: why isn't everyone doing it? Well, first of all, building a rocket engine is already ridiculous. You're pumping cryogenic fuel and oxidizer into a combustion chamber at pressures that would destroy most industrial equipment, then deliberately setting the whole thing on fire and hoping it survives. Few operational engines have ever pushed much beyond the 250 bar range. Raptor has been pushing far beyond that. Higher chamber pressure is basically free performance. If your engine can survive it, the problem is that every increase pushes temperatures, turbopumps, seals, cooling channels, and turbine blades closer to destruction. Imagine blowing up a balloon until it's almost ready to pop. Now imagine keeping it there continuously while it's also on fire. That's the kind of game modern rocket engineers are playing. Let me go into more detail on what actually makes Raptor special, because this is the part most people miss. The real breakthrough isn't the thrust number, it's the engine cycle. Raptor uses something called full flow stage combustion. For decades, engineers viewed this as one of the holy grails of rocket propulsion. On paper, it's incredibly efficient. In reality, it's incredibly difficult to make work. Instead of throwing propellant away to power the turbopumps, virtually all of the fuel and oxidizer flow through separate pre-burners before reaching the main combustion chamber. In other words, almost every bit of propellant contributes to thrust. And then there's the fuel. Raptor runs on methane, not kerosene. That matters because methane burns much cleaner, reducing the soot and carbon buildup that can plague reusable engines. It doesn't eliminate maintenance, but it makes rapid reuse far more realistic. The entire Starship business model depends on that idea. Fly, land, refuel, and fly again. And the vacuum version of Raptor pushes the concept even further. With its giant extension, it can achieve around 380 seconds of specific impulse in vacuum, putting it among the most efficient chemical rocket engines ever built. And this brings me to the real secret behind Raptor. It isn't genius, it's iteration. Raptor 1 looked dramatically more complicated than the engine we see today. Pipes, shielding, external hardware, complexity everywhere. Then SpaceX started deleting things. By Raptor 3, engine mass had fallen from roughly 2,080 kilograms to about 1,525 kilograms, while thrust increased dramatically. Think about that for a second. Most engineering projects become more complicated as they improve. Raptor became simpler. The engine went from looking like a collection of parts to looking almost sculpted from a single piece of metal. That's one of the most underappreciated achievements in the entire Starship program. And SpaceX isn't developing this technology in isolation. Blue Origin's BE-4 uses methane. China is aggressively pursuing methane-fueled launch systems. Across the world, the industry is moving towards similar propellants. But today, no operational methane engine combines Raptor's level of thrust, chamber pressure, and full-flow stage combustion architecture. If future Raptors really reach 300 tons of thrust, a super heavy booster with 33 engines would approach 10,000 tons of total force at liftoff. For comparison, the Saturn V generated roughly 1/3 of that. The scale is difficult to comprehend. Raptor 1 produced about 185 tons of thrust, Raptor 2 pushed that to roughly 230, and Raptor 3 reached around 269 to 280 tons of thrust. And the next target being discussed publicly is 300. Those sound small? They're not. Rocket performance compounds. 30 extra tons on one engine becomes nearly 1,000 extra tons across an entire booster. That can mean heavier payloads, more satellites per launch, more propellant delivered to orbit, and ultimately more capability for lunar and Mars missions. But here's the uncomfortable possibility. Maybe they don't get there. Maybe 300 tons proves harder than expected. Maybe the materials hit a wall. Maybe thermal margins disappear. Maybe the engine finds entirely new ways to fail. SpaceX has lost numerous engines during development over the years, and pushing deeper into the limits of pressure and temperature only make the challenge harder. The difference is that SpaceX treats failure as part of development. Every test generates data, every anomaly exposes a weakness, every redesign teaches something. So what happens if SpaceX succeeds? Then Starship stops looking like a prototype and starts looking like infrastructure. Launches become cheaper, payloads get heavier, and the cadence increases. And missions that sound impossible today start looking routine. That's why the story isn't really about Raptor 4. It's about what happens when rocket engines stop improving incrementally and start improving exponentially. The real breakthrough isn't 300 tons of thrust. The real breakthrough is that SpaceX keeps finding ways to make the engine simpler, lighter, more efficient, and more reusable, all at the same time. And if they pull that off again, the rest of the space industry is going to have to respond. Thank you for watching, and if you enjoyed the video, consider subscribing.